So today we continue our walk through wastewater treatment, and we are talking right now quick little bit on tertiary treatment. So we've covered primary treatment, secondary treatment. Tertiary treatment is defined as basically anything beyond secondary treatment except disinfection. So a lot of treatment facilities will have a secondary treatment process followed immediately by disinfection. The city of Newburgh is an example of this, but other facilities may add a step there. And the two typical things that you might see are something specific for nutrient removal. So if you have, for example, chemical phosphorus removal, you might have some tanks there where some chemical is added to achieve chemical precipitation of the phosphorus and then filtration. Or some sort of targeted pollutant removal. This would maybe be in the context of filtration. Filtration can also be added for particles in general. There's essentially two main kinds of filtration: depth filtration and cloth media filters. So cloth is essentially filtering through cloth, like cheesecloth, typical things, or fabric. Depth filtration would be sand or granular activated carbon, and these can achieve very high particle removals, resulting in really low turbidity. Turbidity being the measure of how much light scattering there is or how cloudy the water might be. So you see filtration most commonly with UV disinfection, which we'll talk about in a little bit. Ultraviolet disinfection requires that the ultraviolet light can actually hit the bacteria or viruses or whatever it's trying to disinfect, and if there's particles present, it can't do that. And so you need to have really clear water in order to accomplish that, and so filtration is one way to do that. Also, sensitive water bodies, bays, and so forth that might be sensitive to eutrophication may also require additional nutrient removal, which could be accomplished in the context of filtration. So that's all I really wanted to talk about with tertiary treatment. I'm not going to go into any kind of main detail about that. Most of today is talking about disinfection, which is an incredibly important topic in environmental engineering, and it's relevant to both wastewater treatment and drinking water treatment. We're covering it here before we've even really started looking at drinking water treatment, but pretty much everything we talk about today is applicable to the drinking water process as well. So when we're talking about disinfection, we're talking about partial destruction of disease-causing organisms. So bacteria, viruses, helminths, which are worms or protozoa. This is not the same as sterilization, which is the complete destruction of all of those organisms. It's partial destruction. So that can include damaging cell components like the cell wall, or influencing cell permeability, damaging the DNA or the RNA, or affecting enzymes, essentially making it so that these things are not infectious anymore. So you might have a bacteria that you don't kill. The bacteria is still alive, but you damage its RNA, and so if you did ingest it in drinking water, for example, the bacteria wouldn't be able to reproduce in your body. And with the vast majority of disease-causing organisms, ingesting the amount that's in the water, that amount is not going to cause major problems, but it's once they're allowed to reproduce in the host that they can reach levels that can cause problems. And so disinfection is about either killing or damaging to the point where they can't be infectious anymore. From a drinking water standpoint, we have these concepts of the primary disinfectant that we would add to water to initially damage or destroy the organisms. And then we have this secondary or residual disinfectant. So this is before we put the drinking water into the distribution system, we want to put in some residual chemical disinfectant to keep regrowth from happening in the pipes. So we might chlorinate our drinking water and leave some chlorine in there into the distribution system. As opposed to wastewater, where our concern is both public and environmental health, we want to disinfect the wastewater when we're done treating it so that we don't release disease-causing organisms into the environment. But we can't leave a residual disinfectant in the water because we're going to discharge it to the environment, and we don't want to be killing things that are out in the environment. Chlorine is a potent biocide for a lot of different kinds of different kinds of organisms, including fish. And so we want, if we do chlorinate, we need to be able to take out any extra chlorine we have when it's done doing its thing before we discharge. Okay, so that's a little bit of a difference between drinking water and wastewater. If we do something like with UV disinfection, which we'll talk about in a little while, with UV disinfection in drinking water, I can use that, but that doesn't leave a residual, so when I am about to put it into the distribution system, then I'll still need to add chlorine, as opposed to wastewater, where if I'm going to use UV disinfection, I don't need the chlorine at all. All right, so talking a little bit about the kinetics, Chick's Law, 1908. By the way, the red in this document is the missing stuff from the handouts. And I've just copied it in here, so if you want, you can just pause the video and copy it down, or just copy it down while I'm talking, but I didn't want to have to be writing it while I was talking here. So Chick's Law is a really simple first-order differential equation, first-order kinetic law that says the rate of change in the concentration of organisms with time, the change in the number of organisms with time, is equal to negative k, which is an inactivation rate constant, times the number of organisms that are there. So essentially, the disappearance is proportional to how many are present. Simple, first order. We have a lot of experience with these now, and we can integrate them and get a similar equation as what we've seen before. So this says n sub t over n sub 0, in other words, the fraction of organisms remaining at time t, the number that are there at time t divided by the number that were there initially, is equal to e to the negative kt. N sub t over n sub 0 is 1 minus the removal, right? So if my removal is 75%, then I'm only left with 25%, or 0.25 of what I had initially. Right? So my removal is 75%. 1 minus the removal is 0.25, and that would be the number of organisms at time t divided by the number that were there initially. Okay? So what's important to recognize here is that the rate at which organisms disappear is proportional to the number that are there, but also you can see this K, this inactivation rate constant. It turns out that K is a function of the actual disinfectant concentration. Okay, so in addition to time, the concentration of the disinfectant is also important in how fast things go away. So as a very broad, simple example, if I had a bucket of contaminated water and I want to disinfect it, I could add like a tablespoon of bleach. Bleach is chlorine, it's a disinfectant. I add that tablespoon of bleach to the bucket. It might take, say, an hour for that to do its work to disinfect what's in there. Right? So the disinfection, the rate of inactivation is proportional to the time. But if I add a cup of bleach to the bucket, it might only take 5 minutes for complete disinfection. Okay, because again, that the rate at which we have inactivation is proportional both to time and the disinfectant concentration. All right, so how do we disinfect? So there's I'm going to show at the end of the video. I'm going to look at a set of handouts where we can look at some additional information, and those are also published on the G Drive. So I'm going to go to that at the end, but right now, what are the basic methods of disinfection? Well, we've got free chlorine, so that can be added in 3 different ways: chlorine gas, chlorine liquid, or chlorine solid. Chlorine gas, Cl2, has typically been added in the past in the form of chlorine from rail cars. This was more common a longer time ago, becoming less and less common. In fact, almost all facilities have phased this out completely. After September 11th, Homeland Security essentially made it illegal to use chlorine gas on your plant unless you went through a bunch of hoops to allow it. And most facilities have either completely transferred over to a liquid or a solid, or are in the process of it, or have plans to. Sodium hypochlorite is bleach. Bleach that you buy at the store is sodium hypochlorite, but it's a lower purity or concentration than might be added in a treatment facility. It's a liquid. It is somewhat unstable, especially with respect to photo degradation. So the longer you have it, the more it will break down, and especially if it's out in the sun, you will lose disinfection potential over time. So that's the main concern with sodium hypochlorite. And then calcium hypochlorite is a solid. It's not as commonly used as some of the other methods, especially in sodium hypochlorite. That's the dominant method these days. That sodium hypochlorite can be generated on site. So you can take sodium chloride, which is table salt, and put a lot of electricity through it, and through electrolysis create sodium hypochlorite. And you can do that on site with just having a big container of salt and a lot of electricity, and you can create it there. And that's what both the Newburgh drinking water plant and wastewater plant have on site sodium hypochlorite generation. So they don't need to get deliveries of it. Extremely large plants will usually still get deliveries from a central location. Calcium hypochlorite is maybe what you would use in if you have a swimming pool at your house that you want to keep chlorinated. A lot of times they sell these little hockey puck looking things that the water can circulate through and keep dissolving some of that into the pool. Combined chlorine, so in Water 4.0, he's talked about this a couple of times. This is called chloramination. So one thing you can do also if you're chlorinating is you can add ammonia to that process. If it's wastewater, you might already have some ammonia in the wastewater, or you might add it back. If it's just more commonly practiced in drinking water than in wastewater, where you would actually add ammonia to chloraminate. It's a slightly different set of reactions, where instead of just free chlorine, you're looking at monochloramine, dichloramine, trichloramine. These have a little bit, they're not as good of a disinfectant, but the idea is that they create less disinfection byproducts. So you've also read in Water 4.0 about trihalomethanes, haloacetic acids. These are common carcinogens that occur in drinking water, and they occur through the chlorination process when there's disinfection byproduct precursors present. Chloramination reduces the amount of those that are created. However, chloramination can cause production of this NDMA and nitrosodimethylamine, which is an extremely carcinogenic compound. Has been difficult to measure historically, but now we have the technology to do that, and so there's always a concern about that one as well. Okay, so in addition to free chlorine, we can also use chlorine dioxide. Chlorine dioxide is a gas, not nearly as toxic as chlorine gas, but it still is somewhat problematic. And it's also really expensive, so it's not that commonly used, but it is an option. It has its own disinfection byproduct concerns, chlorite and chlorate. Ozone, which is O3, is commonly used in other parts of the world, especially Europe. Ozone systems do not take up very much space. The ozone is generated on site. And so, but it is fairly expensive, takes a lot of electricity to do. It also, if they're not commonly used, you might not have specialists around who know how to use ozone. It can have its own disinfection byproduct problems with bromate. This is only usually a problem when bromide is present, which is typically when you're near the ocean. Essentially, bromide comes from seawater. So if you're way inland, you're not going to have a bromate problem. But ozone, again, like I mentioned with UV, if you're using it for drinking water treatment, which is a common use for ozone, especially in Europe, you still need to add that residual, which is usually chlorine, before you put it in the distribution system. UV, like I said before, requires very good particle removal. Otherwise, it's not effective because, again, you could have a big particle, an organism hiding right behind it, and when the light tries to hit that organism to disinfect it, it's hiding and it's protected. So we have to remove all those particles to make it effective. So those are the main methods of disinfection. There are newer technologies, advanced oxidation processes that use things like peracetic acid or hydrogen peroxide in addition to ultraviolet. So hydrogen peroxide plus ultraviolet is a common sort of state-of-the-art method to achieve very high levels of disinfection, and can also actually oxidize very small organics like pharmaceuticals, for example, that might go down the drain, pass through the wastewater treatment plant. If you hit it with hydrogen peroxide at the end of the process, you could actually oxidize that and destroy it before you release it to the environment. So depending on the situation and how sensitive it is and what you have in your wastewater, you could add other things in your disinfection process to help with removals. All right, so what does the chemistry of the chlorine look like? I've just copied in the reactions here. You can pause it and write this down if you'd like. The basic reaction here is we've got, I'm writing this as chlorine gas. So if you had chlorine gas, Cl2 combines with water to make this HOCl plus H plus Cl minus. HOCl is our disinfectant. So if we're using sodium hypochlorite, which is NaOCl, we put that in the water, the Na comes off, and then we've got the OCl that can then combine with the H to make HOCl. If we're using chlorine gas, it's actually going to combine with the water to make the HOCl. HOCl is our disinfectant. That's the one we want. So we can look at this reaction and we can write an equilibrium constant for it. This is the acid-base reaction going on with HOCl that I was just talking about. So we add NaOCl, we get this thing, and now we can create the HOCl. Again, remembering our acid-base stuff, if we write our Ka for this reaction, we get this. And what we can find by using some of our acid-base stuff that we've learned before is that given where this Ka and the pKa is, it turns out that when the pH is greater than about 7, you're going to have more of this OCl minus, the base form, versus when the pH is less than about 7-ish, we'll have more of the HOCl, the acid form. HOCl is our disinfectant that we like. OCl minus is a disinfectant, but it's not a very good one. It's about 100 times less potent of a disinfectant as HOCl is. So it turns out that if we want to get good disinfection, we need to have our pH typically less than 8 or 7 if we want to get good disinfection. If our pH is 9 and we try to chlorinate, we're not going to get good disinfection. We're going to need a lot more chlorine and a lot more time to achieve what we want to achieve. So you'll see that come up in just a minute. How do we actually put this into practice if you wanted to disinfect at a treatment facility? And how are the regulations written to make sure that we're disinfecting properly? It comes down to this CT concept. And CT essentially stands for chlorine time, and the units are milligrams minutes per liter. And it's the chlorine concentration, how much you have in the disinfection process, times the time that you're giving it. Okay, so again, I talked about how the disinfection is proportional to the time and the concentration. So we're going to multiply those together to get this CT factor. And the regulations are written to require a certain CT in order to achieve good disinfection. So let's look at some tables that summarize that. All right, so these are tables that say the CT log inactivation values in milligrams minutes per liter for Giardia, which was one of our protozoa. It's the protozoan that is probably most difficult to destroy, and if you can destroy or inactivate Giardia, you're also at the same time destroying or inactivating pretty much everything else. So using free chlorine at a really cold temperature. So if you're at 0.5 degrees C, this is your free chlorine residual. It's that concentration, the C in the CT part. These are the pHs you're at. If you're less than 6, 6.5, 7, or 7.5, 8, 8.5, or greater than 9. There's this concept called the log inactivation, and I'll show you an equation for that in a second. The log inactivation is essentially how much are we removing. If we have 1 log removal, that's saying we're removing 90%. If we have 2 log removal, we're removing 99%. If we have 3 log removal, we're removing 99.9%, and so on. So the higher log removal or log inactivation you have, the more you're removing by a lot. So if I have 1 milligram per liter free chlorine residual and I want 3 log removal of Giardia at 0.5 degrees C at a pH of 6.5, I would look in this one row over at pH 6.5, and I'd see that I need 176 CT in order to do that. Now my C was 1 milligram per liter, thus I would need 176 minutes to achieve 3 log removal of Giardia at pH 6.5, temperature of 0.5 degrees C, and 1 milligram per liter of free chlorine residual. And you can see that as the pH goes up, I need more and more CT, because again, more of my chlorine is going to be in the OCl minus form, less in the HOCl form. As the temperature goes up, I need generally less time. So on the next page, I'm up at 5 degrees C for the same thing I just looked at, which is 1. This number is 125. Right? As the temperature goes up, reaction rates also speed up, and so I need less time for it to happen. As my free chlorine residual concentration goes up, my time required is, my CT is actually going up, but the time is actually going down. So let's look at an example. Here I had 125 for 1 milligram per liter, 3 log removal. If I go to 2 milligram per liter, the number is 138. But that's the CT. It's not the minutes required, it's the CT. Concentration times time. My concentration is 2. So now my actual time required is going to be 138 divided by 2, which is what, 69 minutes is what I would require in this case. So my time has gone down by a lot because my concentration went up. Again, that's affecting that K, the rate constant, when my concentration goes up. Okay, so these tables, there's a bunch of them here. I put these also in the folder that you can look at. This is a common way that governments regulate how much disinfection is required. So they might say you have to have 2 log removal of Giardia or 3 log removal of Giardia. So when you're designing your disinfection system, you would design it for the conditions you have to meet these requirements, these CT values. Okay, so that's these tables. In the U.S., there's EPA regulations. They're called the Stage 2 Disinfection Byproducts Rule that govern the CTs required, as well as technologies required for disinfection and for just treatment in general, as well as rules to limit disinfection byproduct formation. Okay, that is most of what I wanted to cover on disinfection. Now there's a video, a separate video where I do an example problem that analyzes and sort of designs a very simple disinfection system, so you can see how a CT approach applies to a simple system. Okay, a couple other things actually, so I'm not done. I want to just talk about the developing world applications a minute and then go through some additional resources on a handout, on a separate handout. So developing world applications, I'm making a specific point of it in this lecture because in the developing world, a lot of times our primary concern if we're trying to work on water and wastewater sanitation type technologies is disinfection. We want to eliminate these acute diseases, biological things that can cause illness. Here in the US, we don't deal with that as much, and so a lot of times what we're worried about is metal pollution or pesticides or some organics or metals or something, carcinogens, longer term exposure type situations. In the developing world, we're much more concerned usually with disinfection. And so the technologies are a little bit different there. I wanted you to just see what some of them are. They're the same concepts at a much smaller or decentralized scale generally. We'll look at these on the handout here in a minute, but you've got chlorination pots for wells that use calcium hypochlorite, mini dose, which is a liquid bleach doser, or tablet feeders, gravity tablet feeders. And there's a lot of self-contained UV systems that you can just put in line in a drinking water system. People use those at their homes and on their wells and stuff too. And then in decentralized, we have chlorine or iodine. People, maybe if you've gone camping, you might have chlorine or iodine tablets that you add to your water. You could boil the water. That's a really effective way of disinfecting. It just takes a long time and takes a lot of energy. Okay, so let's look at some handout material. This is a table from your book that looks at different kinds of disinfectants, free chlorine, chloramination, chlorine dioxide, ozone, and UV light, and looks at how effective they are at disinfecting these different kinds of organisms, how common they are, residuals. This is all from the drinking water chapter. And then disinfection byproducts that are of concern. And then this is a similar table from the wastewater literature. So again, looking at the different disinfectants across the top, different characteristics of them down the side. So chlorine is low cost, whereas some of these others are higher cost. You can look at like safety concerns, toxicity to microorganisms, different kinds of things, characteristics of the different disinfectants. This next table shows CT values required for login activation using different disinfectants and for bacteria, viruses, and protozoa. You can see UV because it's not a chemical and you can't have a concentration. It's got a little bit of a different unit. It's millijoules per centimeter squared. So we're not going to talk a lot about that, but it's kind of a similar sort of thing as the milligram minutes per liter. So you can see for chlorine, it's really good against bacteria, 0.1 to 0.2 for 1 log removal, whereas chloramine, the chloramination process, not as effective of a disinfectant. You need a lot more in order to achieve the same removals. And then we can see viruses down here. Same is true for viruses. Same is true for protozoa. And also note that viruses take more CT than bacteria do to disinfect, and protozoa take a lot more than viruses or bacteria in order to disinfect. And this is mostly because those protozoa, Giardia and Cryptosporidium that we talked about in the water quality lecture, form these cysts around them that sort of protect them from the outside world, and it takes a lot to get through those. This is just a pH, essentially a fraction versus pH diagram that shows, after you get past 7.5 pH, the OCl minus dominates up here, whereas below that pH, the HOCl is going to be a much higher fraction. So this gives you an idea of the pH range and what's going on for effective chlorination. This is an aerial view of a wastewater treatment plant that I just wanted to point out some features of. We're now nearing the end of the wastewater material, so we should know essentially what the process looks like. Here's a plant where we see two big oxidation ditches, two secondary clarifiers that those go through. And then the wastewater goes through some filtration here, and then on its way to this facility up here. Down here you can see there's some tanks, and these are chemical storage tanks that store the liquid bleach as well as the dechlorinator, which is, I can't remember what it is in this case, but I'll think of it in a few minutes. So on the way from the filters to here, it gets disinfected by the bleach. And this is a chlorine contact channel, where if you look closely, you can see it comes in. There's two channels here, one on the left, one on the right. The one on the right in this view is dry, and the one on the left is being used. Wastewater comes in here, goes all the way down this channel, turns, comes all the way back, turns, comes all the way back. So this is a common orientation that uses complete plug flow in a small area and makes the wastewater snake around. Gives the chlorine a long time to do its thing, and also achieves plug flow, which we said before is good for reducing the size of the reactor needed to achieve the removals required. And then up here is the dechlorination system. And this shows that in a more schematic way. You can see the chlorine contact basins here. These are the hypochlorite storage tanks and metering. So the sodium bisulfite is the dechlorinating agent and added back at the end before the wastewater gets discharged to the Cascade aerator, the little waterfall, and then down into Marsh Creek. Some is also used in this system for recycled water irrigation, and so that goes into this hydropneumatic tank that's then pumped back into a non-potable water system for irrigation. This is what a UV system looks like in real life. There's wastewater channels down below this platform, and so the wastewater is flowing down this way. These are access panels where you can open these up, and then a crane, there's a bar up here, a crane goes down on here and can go down and grab the bank of UV lights and pull them up for maintenance and access. So this is really common as far as what a UV system might look like in real life. And then these are the technologies for developing world applications. This is a bleach pot where you have a sand and bleaching powder mix. You could lower this down into a well, and as you use the water, it's disinfecting the water in the well, and then as you use it, the water kind of has had time to be in contact with chlorine that's gradually coming out of here. This is the mini dose, so this pulls, it's not powered, but it uses the actual the velocity, the flow of the water coming through there, through the mini dose, to pull bleach in and mix into solution. These are really common in developing world applications, really cool little devices. This is a UV self-contained Hallet system that the water just goes through. You plug in a pipe on this end, you just need to power it, and it doesn't actually take that much energy. I have a couple in my lab, a couple little 60 watt and 100 watt UV systems that can have a decent flow rate through them and still do a pretty good job of disinfection. This is a gravity-based tablet feeder where you can put tablets of calcium hypochlorite in there and the water goes past them in this tablet feeder. This is similar to what you might see in a swimming pool, but you can also use it in drinking water applications. And then this is a Sawyer filter. Sawyer filter is something you can buy at Walmart for backpacking and so forth. It's a pretty neat technology that has come on the market in the last 10 years, where the nominal, typically with filtration devices, you have a nominal pore size that is maybe the mean pore size in a filter. And what that means is if I had a mean pore size of, say, 0.1 microns, some things there will be some pores in there that are greater than 0.1 microns, even though the mean size is 0.1. So if I had a microorganism that was 0.2 size, 0.2 microns, it wouldn't fit through most of the pores, but it would fit through some, and that could be bad if that microorganism is harmful. What Sawyer did is they said, we have a 0.1 micron pore size, but it's an absolute max. So all of the pores are that size or smaller. And 0.1 microns is small enough that no bacteria can get through. Pretty much all bacteria are greater than 0.1 microns in size. They're closer to 1 micron. Now viruses, I think, are around 0.1 micron, and so some of them can maybe still get through here, but a lot of them can't. And so this is not a disinfection technology, it's a filtration technology, but it achieves removal of most disease-causing organisms. We don't know yet kind of how durable these are and whether they would last a really long time, and it's also difficult to know that they're doing what they say they're doing, i.e. that they're not damaged. In a chlorine system, you can measure how much chlorine is there, and we have the research to demonstrate to us that we know if you have this much chlorine in this much time, you're achieving good disinfection. So if you can just measure the chlorine and measure the time, you know you're achieving what you're trying to achieve. With a system like this, it's very difficult to do all of the microbiological work necessary to know that you're achieving good disinfection or good removals, especially in remote applications or in developing world applications. So those are just some additional resources to support the lecture. Take a little bit and look at the example problem video as well. And I think that wraps up most of disinfection. So the last part of the wastewater treatment is just going to be solids handling, and then we'll move into drinking water treatment. And again, we've gone through a lot of processes in the context of wastewater that will cover drinking water processes as well. So there will be less of that.